Everyone for coming, and thanks Bill for introducing me. I've been using eXtreme gradient boosting off of Bill's large data set of tabular data that spans since the 90s, which has follow-up data and a significant amount of clinical data. And I've been using that to try to predict outcomes, fracture outcomes specifically, just using ICD-10 codes that have been tracked on the patients as well as medications that have been administered. So first, there's a brief overview of osteoporosis in Canada. So there's been a significant amount of money going into osteoporosis care. It's 1.3% of all of expenditures in 2010, based off of this paper that Bill and Lisa and everyone wrote. But it's $2.3 billion, so it's a significant amount of money that's going towards the care of both the acute fracture event, and then it goes up to $3.9 billion if you include the cost of subsequent long-term care facilities. Currently, right now, all 65-year-old females are suggested to get this scan, and based off Statistics Canada, that's about 200,000 people will be getting this scan at age 65. And that scan, of course, is bone mineral density testing to determine whether that person has osteoporosis and to try to come up with a FRAX risk score to try to determine what their future fracture risk is in the next 10 years for hip or major osteoporotic fracture. The thing is, only 20% of North American women older than age 65 are osteoporotic at the femoral neck or lumbar spine. And so my thought is, if you could use the ICD-10 codes and medications that were administered to the patients, would you be able to pre-stratify patients that are at higher risk and stratify out patients that are at very low risk in a way to try to avoid unnecessary testing and unnecessary bone mineral density testing by testing every 65-year-old female in Canada? So there's quite a few algorithms that will predict hip or major osteoporotic fracture risk. Obviously, the main one is FRAX. There's several other algorithms as well. FRAX and Garvin both can incorporate bone mineral density. Q-Fracture and FREM are more administrative type data and clinical risk factors. So I'm sure most people here are aware of the FRAX variables, but they include age, which is one of the strongest variables as well. They include femoral neck BMD, gender, height, weight, prior fractures, hip fractures in the parents, smoking, glucocorticoids, secondary osteoporosis, rheumatoid arthritis. So these are all obviously variables that have a fair amount of signal in them and therefore can be aggregated amongst different jurisdictions to try to create an aggregate score for future fracture risk. Secondary osteoporosis is defined as insulin-dependent diabetes, osteogenesis imperfecta. There's just a variety of secondary osteoporosis conditions that are all lumped together in FRAX to try to create an aggregate risk score in different countries. Garvin also includes other variables such as falls, and they include the number of fractures in the last 12 months. And they're included as categorical variables as 1, 2, or 3 or more events. So there's some signal there as well. Q-Fracture, as I mentioned, doesn't incorporate bone mineral density, but they do incorporate even more clinical risk factors like dementia, cancer, asthma, COPD, cardiovascular conditions, chronic kidney disease, Parkinson's, epilepsy, antidepressants, and estrogen replacement therapy. So as you can see, there's maybe some suggestion that more is more when it comes to nonlinear algorithms that are able to detect multiple different variables and predict accurately without worrying as much about collinearity. So there's a Danish FREM, which is fairly new from 2018. They basically took 606 ICD-10 codes in women and 536 ICD-10 codes in men. And then they applied backwards selection to create a logistic regression model. And they ended up using 38 diagnoses in men and 43 variables, ICD-10 codes in, 38 in women and 43 in men to create the final predictive models for hip and major osteoporotic fracture. So they found that with this approach, they did have some lift compared to an age-only model, and they increased their receiver operating characteristic curves and the area under the curve. So this is essentially a success. So ultimately, what's the point of predicting future fracture risk? Well, one of the main reasons is primary prevention using drug therapy, in that if you can identify those who are at the highest risk and then decrease their risk ahead of time using a variety of anti-resorptive or anabolic approaches, then hopefully you can reduce fractures, which, as I outlined before, can be quite costly at around $21,000 for a hip fracture, for example. So then this is my attempt. FREM obviously is using logistic regression. Logistic regression is pretty good, but I decided to do a similar approach using extreme gradient boosting. Extreme gradient boosting is one of the top algorithms for tabular data. Obviously, deep learning is superior when it comes to unstructured data and image recognition, but extreme gradient boosting is still one of the Kaggle winning algorithms when it comes to tabular data in particular. And obviously, Bill has collected an immense amount of tabular data. So similarly, I used a lot of ICD-10 codes for hospitalizations and appointments, as well medication prescription data. And in turn, I was able to take just a large amount of variables that were in the data set. And then the real beauty of this is the only reason that one of these variables is in the data set is because Dr. Leslie at some point thought that he could write a paper on it. And so pretty much every variable in the data set has at least some base validity for why it's included as a potential osteoporotic fracture risk factor. And so in that way, it's actually a heavily populated data set of medications and conditions that all likely have some minimal collinear interaction for predicting future fracture risk. So that's one of the strengths of the current data sets, whereas in the case of FREM, it essentially took 1,700, I think, were the original number of ICD-10 codes, and then about 900 of them were removed just because they had less than 1% availability in the patient data set. But the point is, you started with a lot of variables that may or may not have been valid. And so that's okay from a machine learning standpoint, but obviously the better feature engineering and data selection you have at the outset, the better your outcome will likely be. So in this case, it included quite a few different variables and medications, including psychiatric medications. So some of the psychiatric medications can probably be risk factors for fall. They can also be risk factors for vitamin D issues when it comes to epileptic medications and these sorts of things. Cardiac medications were included in the data set. Again, things like calcium channel blockers might have some actual effect on calcium status. However, they may also just be surrogate markers for death. I included remote anti-osteoporosis therapy. So because my intent is to use this tool to identify patients who are at risk for fracture prior to their first bone mineral density test, I did not want patients currently on anti-resorptive therapy. So I removed any patients who had been taking anti-osteoporotic medications in the 2 years prior to their first bone mineral density test. I included a variety of steroids in their various forms, some endocrine medications, such as for hyperthyroidism and hypothyroidism, hormonal therapies, aromatase inhibitors, estrogen replacement, anti-androgen therapy in prostate cancers, as well as a variety of gastrointestinal medications like PPIs, medications associated with diabetes. Then I included a variety of new clinical risk factors as well. As you can see here, there's quite a few dementia type conditions and multiple sclerosis, Parkinson's, systemic conditions, muscular dystrophies, which could be surrogate markers for fall again, connective tissue diseases. Again, the beauty of this data set is all of these probably have some minimal contribution or large contribution to predicting future fracture, osteoporotic fracture risk, or they just wouldn't have been in the data set to begin with. So the other beauty of it is I was able to predict all independent fracture type. So this includes vertebral, humeral, wrist fracture, pelvic fracture, femoral fracture, and then there was also just a fracture category called other, which is just a grab bag of fractures. And so what is this really missing? To make sure that it was purely an administrative fracture prediction tool. It does not have any bone mineral density values, although I am able to add all of the bone mineral density values that come from the scanner. As well, it doesn't have the patient's height and weight. It doesn't have really anything where you would ask a patient, hey, has this occurred to you? It's all based off of the ICD-10 codes. I am working on a second algorithm now that does include bone mineral density at all available sites rather than just the hip. And it's been reasonably successful, but that's for another day. So for patient selection, as I mentioned, I wanted to make sure that they were not currently on anti-resorptive therapy for the 2 years prior to scan acquisition. I only wanted to train off of the first available scan, so I removed all patients where it represented a follow-up scan to try to remove any bias secondary to therapy that had occurred based off of the first scan. And I removed patients who didn't have at least 2 years of follow-up prior to censoring without a fracture event. So I started with 158,000 rows of individual scans between the 90s and 2018. 60,000 of these were follow-up scans, which were removed. 20,000 scans were removed that didn't have enough follow-up. As well, I got rid of all patients less than 50 years of age, as I felt that that wasn't relevant for the question at hand, which is, should women age 65 all be getting bone mineral density testing? And then, yeah, 16,000 patients had had prior recent anti-resorptive therapy, and they were removed. With respect to feature selection, I got rid of highly collinear variables, particularly when I was working on the one that included bone mineral density data, as T-scores, Z-scores, BMDs are all quite collinear, but obviously that's not relevant for admin fracs as much, the current administrative data. I got rid of data that was highly missing. I did some minimal feature removal using the Baruda algorithm, in that it was able to tell me whether there were certain features that just had no association with the outcome of interest. And then all numeric variables were normalized and centered and scaled. Right skewed variables were log transformed, and all categorical variables were dummied. Yeah, as I mentioned, I log transformed all of right skewed variables and centered and scaled to normalize the data. So as well, there's some derived variables that were added. For example, there's a Statistics Canada survival probability that's just based upon 5-year age ranges and gender. So I just entered that in a priori, even though it maybe isn't applicable to every individual patient. It gives some general idea of how long they might live. And then I created Cox proportional hazard models within the training data only. And then I basically tried to aggregate together certain classes of medications, and I also tried to predict death using a Cox proportional hazard model. So essentially, I created one Cox proportional hazard model that was based off of medications that were likely to reduce fracture risk, like hormone replacement therapy and bisphosphonate usage. I aggregated medications that were likely to increase fracture risk into a Cox proportional hazard model, including steroids, aromatase inhibitors, antiandrogens, insulin and diabetic medications, and anticonvulsants. And then finally, I made a third Cox proportional hazard model off of the training data only, looking at that generic survival probability for Canadians based off of 5-year age ranges, their age, home care, COPD, diabetes, chronic kidney disease, chronic liver disease, various cancers, the number of recent hospitalizations, dementia, heart failure, cardiac dysrhythmias, cerebral vascular disease, and acute coronary syndrome. So the idea here, again, is just to try to give an approximate measure of the patient's probability of dying prior to having a fracture. And then after I had dummied out the variables and added any feature engineered variables, there were 612 features tracked. And then all of these features can be calculated directly off of the administrative data sets that can be acquired in Manitoba. Similarly, these data sets could be recreated in other provinces in Canada with some effort, but the point is ultimately it could be done with code, and a lot of it is pre-existing SAS code And so this could be applied to other jurisdictions. As usual, I did a test train validation split. So I trained off 60%. I set aside a 10% testing data set, and then the final validation cohort was 30% of all of the available first scans. So this is another strength of my approach. I was able to create 6 different extreme gradient boosted algorithms that predicted each fracture type. So my thought process behind this is that you might have slightly different risk factors for vertebral fracture versus hip versus wrist versus humeral fracture. And so by creating independent models and then ensembling their predictions in parallel, each model might actually detect risk factors associated with each fracture. So instead of trying to lump together all fractures as a single major osteoporotic fracture event, I was able to predict off of each fracture type and try to discover some of the variables that are associated with each fracture type in a more granular way. I felt that this was also meaningful because ultimately I'm training off of the fracture date using survival models and Cox proportional hazard modeling and negative log likelihood as the optimizer for my extreme gradient boosting algorithm. So it didn't have a lot of face validity to call a hip fracture the same as a vertebral fracture, as the same as a random fracture or a wrist fracture. So I thought that this might be confusing to the algorithm in that there could be quite a bit more signal for somebody who has a hip fracture than for somebody who has a wrist fracture or a rib fracture, for example. And so I thought it was important to train the algorithm based off of apples to apples comparisons, AKA the date of vertebral fracture or the date of hip fracture, rather than calling those different types of fractures the same, which clearly they're not. So as I mentioned previously, I trained one for vertebral, one for hip, one for pelvic fracture, one for wrist, one for humeral fracture, and one for other fracture. To identify the optimum weight to assign to each of the algorithms, I use Bayesian optimization. So that essentially I just assigned a weight, like a random weight, to each of the 6 different extreme gradient boosting algorithms. And then I applied some Bayesian logic to basically find the best weight to apply to each of the 6 algorithms to come up with the best area under the curve for predicting major osteoporotic fracture, as in all major osteoporotic fractures. So I feel like that's one of the strengths of this approach. So fractures are rare events. Rare events and unbalanced data sets are not good for artificial intelligence training. So if you take all of the fractures, there were 13% fractures within the overall data set. However, I'm training off of each individual fracture type, and so that drops it down to low single-digit percentages for each fracture type. So obviously the problem here is you could have a 98% accurate model that just says no fractures happened. And so that would be a parsimonious or mathematically parsimonious algorithm, but obviously clinically completely useless. So the problem is, how do you take a rare event in the 2% range and then make the algorithm able to detect the underlying risk factors in that minority group? And so I did this through synthetic minority oversampling. So essentially, I use the RSLS, relocating safe level synthetic minority oversampling technique. I took the 2% or 3% undersampled class, and then I basically attempted to find the underlying characteristics of that class. And then I created artificial instances of that class to make the data set more balanced so that it was easier for the extreme gradient boosting algorithm to find the relevant features. As well, in the training data set only, I imputed missing values using random forest imputation. So in this case, I also had to pay some attention to when the fracture occurred. So I had to make sure that if I was calling it a pelvic fracture, that it was either only a pelvic fracture for that patient, or that the pelvic fracture was the first fracture that occurred in that patient, so that I was predicting the right time of fracture and not some fracture that occurred after a vertebral fracture or a hip fracture. I wanted to make sure that I was predicting the first fracture event. So then there are multiple parameters that can be tuned in the extreme gradient boosting algorithm. Because I was making 6 ensembles, I didn't think it was reasonable for me to manually tune each algorithm. And so instead what I did is I did a random hyperparameter search. It's not computationally parsimonious to do this, but it's good for my time in that I can basically just start the computer running and come back next week and have an answer. So I did a random search using 5,000 iterations. I applied early stopping criteria. So if there is no improvement in the area under the curve for predicting hip or major osteoporotic fracture within 500 iterations, then I stopped the loop and went on to the next extreme gradient boosting algorithm to train off of the next fracture type. I stratified the fracture dates based off the date of fracture. So I did a 10-fold cross-validation. And basically, I lumped together the date of fracture into categorical times. So I'd lump together, fractures within 2 years or 5 years or 10 years in 10 different groups when doing the cross-validation. So here's some example of the more granular feature importances. So here are the 6 different graphs of the features for each different fracture type as per the extreme gradient boosting algorithm. So in the case of most of the fractures, obviously age is one of the top predictors, as well my Cox proportional hazard models that again were trained only off of the training data, not off of the global data set. They were highly predictive. So obviously anti-resorptive medications or medications that are known to lead to increased fracture risk were very high in the extreme gradient boosting final algorithm. Interestingly, osteoarthritis showed up in quite a few of these algorithms. I wonder if that's either a surrogate for increased falls, or it could also just be a surrogate for age in general. Usually this might have been removed because it might have been highly collinear with age with respect to the osteoarthritic diagnosis. Hypertension is likely a surrogate for death. Interestingly, anxiety ended up quite high in a lot of these algorithms, and benzodiazepines did as well. Now, you might be wondering, why isn't corticosteroids high on the list? It's again because it's included in my Cox proportional hazard models. And so I think benzodiazepines are probably also surrogates for falls. And so, yeah, there's slightly different top 10s for all of the different algorithms. History of non-traumatic fractures showed up. I thought that COPD was interesting for vertebral fracture risk factors in that it could be due to these patients requiring prednisone therapy intermittently. However, it could also be due to patients having COPD getting way more chest radiographs, and therefore the vertebral fractures that otherwise would have been undiagnosed getting diagnosed. But I think the take-home message here is when applying 600 different variables, you don't know for sure whether it's correlative or causative. You don't know for sure why the signal leads to the final prediction. These are still largely black box models. But ultimately, what matters is the final accuracy. Yeah, so again, history of anxiety. Interesting that you see that higher up for wrist fracture. So again, this might suggest that benzodiazepines secondary to anxiety lead to more falls, because obviously wrist fractures happen more due to falls on outstretched hands. Whereas if you look at vertebral fracture, I guess those aren't as likely to be secondary to a fall. It's more likely just due to age and illness and how many chest radiographs you get. And of course, I like that a risk factor for wrist fracture is prior wrist fracture. Anyways, the long story short of it is that you have different breakdowns for all of the different fracture types for what is the most relevant variable. So then I ensembled them. So Bill's question was, would the ensemble just find the relative prevalence of each fracture type? And the answer is sort of, but not entirely. Basically, the best algorithm will be weighted based off of prevalence, because obviously the more prevalent the fracture is, the more likely you are to detect it with the algorithm. But the second reason would be if the algorithm was able to detect the underlying features better for a certain fracture type than for another fracture type. So in this graph here, you can see the relative prevalence of each fracture type in this data set. And then you can see how much weight was assigned to each of the extreme gradient boosting algorithms for this fracture type. So you can see here that in the case of vertebral fracture, it felt that the algorithm was more meaningful than the relative prevalence of vertebral fracture in that it gave 32% weight to detecting the vertebral fracture outcome with that extreme gradient boosting algorithm versus only 13% prevalence. And then interestingly, although other osteoporotic fractures were quite prevalent at 22%, after Bayesian optimization of the weight, it didn't like that extreme gradient boosting algorithm at all. And so I presume that this is because there's just too many risk factors for detecting any random grab bag of other fractures. And the other possibility is just, so there's one of two possibilities. One possibility is that it couldn't detect the underlying signal because the outcome is too disparate. And the other possibility is just that these fractures aren't even truly osteoporotic fractures, that they're just a random grab bag of other fractures that are not as predictable as the osteoporotic fractures. So here's the ROC curve. Ultimately, it ended up having similar performance with an area under the curve of 0.74 using administrative data only and not using any bone mineral density data. So it was pretty similar to some of the best fracture algorithms that are in use right now. And then, yeah, again, you had pretty good performance for detecting hip fracture with an area under the curve of 0.84. Now, I don't have it in this presentation, but I'm currently working on the next version of this fracture predicting algorithm. So the current version is only using the administrative data based off of ICD-10 codes and any data tracked automatically by the Manitoba Health System. But the next version is taking all of the bone mineral density data acquired from the scanner on the first bone mineral density evaluation. And what's interesting about it is it's actually a bit better for predicting major osteoporotic fracture. And again, I think this is due to the fact that it's looking at every fracture type individually rather than lumping them together. And so in the one that I'm working on next, you see quite a bump in predicting major osteoporotic fracture compared to some of the current algorithms. So ultimately, the point behind this is to get basically a FRAC score-like assessment of prediction of future fracture risk based off administrative data, and then sending out a letter to those people and saying, look, you're at very high risk. You should come get bone mineral density testing so we can get a slightly more accurate risk prediction. Or conversely, saying you are at very low risk. Maybe you don't need to have a scan done until age 70. And so the next step for me is selecting a threshold. So basically, right now I'm just getting continuous numeric data out from the extreme gradient boosting algorithms. The problem is I'm going to have to select a cutoff value to decide who should get a subsequent bone mineral density scan and who should not. And so that is more of an ethical question than a mathematical question, in that the higher you set that threshold, the fewer high-risk people you will miss. And the lower you set that threshold, the more scans you will avoid. And so ultimately, it becomes an economic and an ethical question, in that if each fracture costs $20,000 and each bone mineral density test costs $500, there'll be a certain sweet spot where you will say, okay, I can accept missing 0.1% of the fractures if I can avoid 50% of the unnecessary scans. But then the ethical part of that question becomes, okay, can I accept avoiding 60% of the scans if I miss 0.2% of the fractures or people at high risk for fracture? So that's both an ethical question and an economic question, because obviously fractures are quite a bit more expensive than the individual test, but thousands of people have to get the test before you're going to avoid a fracture. And so the next step for me is to create either a decision tree economic analysis for that 5-year period between age 60 to 65, or a Markov model in order to determine what's the best cutoff value for avoiding the most unnecessary scans while avoiding as many unnecessary fractures as possible. And so that's the next step for me. Anyways, thank you all for your time.
Okay, well, that was great, and thank you for leaving lots of time for people to ask questions. I'll ask you to unmute and then mute so we can keep some control over this. I'll just point out while people are getting their questions together that thanks for the reference to FREM and Garvin, because in fact that's the focus of the work that we'll be submitting to ASBMR this year. I have a meeting with the FREM people tomorrow morning, and last night corresponded with the Garvin people, so we'll have the ability to do a direct comparison on both fronts. So open up any questions. I don't want to hog the time here.
I'm just looking to see if I'm the only person who's unmuted, and it may be that I am. So Rob Belshaw here. I just wanted to say thank you. That was really interesting. A fun data set to work with, I bet, you know, when you weren't cursing at it. Your last stage where you're talking about, okay, I've got this algorithm which maybe can help us understand is there a shift? Is it sensible to shift the age at which we start to recommend the additional scans? Don't you need to factor in, like, as you're making that decision, don't you need to factor in the potential benefit of the scans? One, does it improve the risk prediction? And you haven't, from the sounds of it, that's your next step, is to figure out, you know, can the scans be, can additional scans add to the information you've got already? Yeah. And then two, how much, if you can predict a patient is going to be at higher risk, how much benefit do they get from being identified as high risk so that they get more intensive supervision, treatment, preventive care? Yeah. And maybe that's what you were talking about when you said a sort of a decision tree model for the period following. Yeah, okay.
Yeah, you're absolutely right. So I'm going to do that with a cost utility analysis. My master's supervisor is one of the gurus for economic analysis in Canada. His name is Doug Coyle. But yeah, you have to do it as a cost utility analysis. So you're right. You need a couple of transition states. One transition state is identified as high risk post bone mineral density. And then the next transition state is they did something about it. Yeah. And then the next transition state is, and we think that the thing that they did reduced their fracture by X amount. Yeah. And so, yeah, you're absolutely right. You have to do that with sensitivity analyses as well. So you can pick and say, hey, I think it's going to decrease your fracture risk by X amount. And then basically you have to model that as a distribution for, we think it's X amount plus or minus this amount. And then the next step is to do Monte Carlo sampling of that and then try to come up with overall sensitivity analyses for all of the assumptions that are needed there. So obviously lots of assumptions are needed to make that determination, which is why economic analysis is the best for answering that question, because you can find a lot of individual data points and then input them into the model for your best guess as to how many people would actually pursue treatment. And then of course, the other problem with that is we don't know whether somebody who's told, hey, we did this highly, accurate, highly detailed artificial intelligence assessment of your risk. Do you want to take therapy? We don't know if that's going to be the same as somebody where they're just told, hey, we think you're probably going to break a bone maybe at some point in the future. We don't know if that's the same amount of people that would subsequently take therapy, but all you can really do is assume that it will be about the same amount and that patients won't really care about the razzle dazzle artificial intelligence portion. and then model a distribution around what percentage of people you think will go on therapy, model a distribution about how much you think that that's going to help. And then, of course, the other problem with that is there might be a different amount of improvement for different fracture types, and there might be a different amount of improvement for future therapies. And so it just comes down to how granular do you want to be in your model. But then all it really comes down to at the end is, because I actually have Kaplan-Meier curves of the subsequent fracture events, I can basically try to strip from those curves what the transition states will be in the Markov model subsequently of the actual people that were predicted to be high risk or low risk. So the ultimate way to solve this problem, I think, is to create a Markov model that's the generic case where everybody gets scanned at age 65. And again, you have to come up with a percentage of how many people actually will get scanned at age 65, because there's definitely going to be a certain proportion that don't bother. But so you create that base case model of no stratification ahead of time. And then you'd create the same model, but what you would do is take the Kaplan-Meier curves for the predicted high risk and the Kaplan-Meier curves for the predicted low risk, because you actually know what happened to those people subsequently. And then what you would have to do is say, okay, so from that KM curve, I think that the transition from state to state is going to be lower in the low risk group because that's what we saw. And I think that the transition from state to state is going to be higher in the high risk group because that data is also available in the data set. And I think that's the closest that you're going to get to answering this question. Obviously, there are some issues with it still, in that it could be that in the future, the high risk group will actually get treated differently because of the physician saying, oh, we already know they're very high risk, so obviously we should push drugs. But again, that's why all you can do is model, make your best guesses, create a distribution around it, and then come up with some cost acceptability curves for what you think the best cutoff should be for scanning versus not scanning.
Well, I think I pushed a button there. Wow, that was
that's a short answer to the question, right?
You've done some thinking about that.
Yeah, I mean, the long story short is it's going to be a nightmare, but it's going to be an achievable nightmare. Like there's clear steps that will lead to a mathematical solution for what cutoff to use.
Thank you.
Yeah, thank you.
I have a quick question. So, I mean, very impressed, very, very nicely done and well thought throughout the different steps to really optimize the outcome.
Thank you.
Yet, I'm quite surprised about the area under the curve, the end results.
Yeah.
We could have expected that with that, like a huge, I mean, it's like a big process, everything. And at the end, we're just like barely above a few points above the classical approach for AUC.
Yeah.
In Manitoba and so on.
Yeah.
So why that? Do you think that bringing the bone or other factor or imaging, could it, in your best guess, could it bring that up to which kind of a level? Or we're reaching the limit of the prediction?
So that's what I'm working on next. I got an AUC of about 0.86 for major when I incorporated all of the different bone mineral density sites. And so I don't know if you will ever get it up to 0.99 or anything like that. I think you probably will not, just because it is such a stochastic event. There are so many different variables that lead to fracture. In this case, I think the reason that it's not better is because I explicitly removed some of the best variables that are variables that get collected upon speaking with the patient. So for example, we have data on how many fractures occurred as reported by the patient. And in the subsequent data set where basically you can incorporate those variables because the patient has come in for a scan, that's when you start getting better area under the curve. I didn't include that in this presentation just because I'm still validating to make sure that the predictions are accurate and that everything was done properly. In that's what I'm working on right now. But yes, I think that I think that there is a maximum threshold. I think that maximum threshold is in the low 0.9 range. And I think the reason that that maximum threshold exists is just that you're trying to predict an event that may or may not occur. It's not clearly due to any one factor. And I agree with you. I think there's probably still more data that I can get out of this administrative data. But as Dr. Katz was mentioning at the beginning, a lot of these ICD-10 codes are pretty good, but not always representative of every single factor that occurs in the patient. I think, for example, if I could include blood work on the patient, you'd get more area under the curve. I think another way to answer your question too is, although it seems like a lot of work, now that the algorithm is trained, you don't actually have to do anything to deploy it on the entire population, similar to FREM. And so another way to answer your question would be, it seems to be a bit better than FREM by about a 0.1 area under the curve. And FREM is the same idea, which is you don't really have to do anything to deploy FREM, despite the fact that it seems very complicated. And so essentially these results are free, would be a way to say it. You don't have to see anyone, you don't have to talk to anyone. You get a risk fracture that's pretty similar to somebody coming in and getting a $500 scan and answering a big questionnaire. And so, yes, I think I could probably still get more area under the curve. Yes, it's still being developed. I think with this administrative only data, I might get it up to about 0.89 or something like that for hip, and maybe 0.78 for major. But yeah, long story short, I think the answer to your question is twofold. Answer number one, yeah, I can probably get it a little bit better. Answer number two, although it seems very complicated, to deploy the algorithm is extremely easy now and essentially free, in Manitoba at least. To redo it in other jurisdictions and other provinces in Canada, there is a clear path for how to do that as well, because it's based off of these codes that are quite generic. And so the algorithm could actually be deployed for a relatively low cost compared to the cost of, bone mineral density scanning every single patient at age 65. And then once it was deployed, be free essentially forever.
So again, that was the short answer. And just so Didier doesn't get the wrong idea, we don't get $500 for doing a bone density in Manitoba. We're off by a factor of 10 on that. But that's
no, I'm not
okay.
talking about what we get paid, but I'm talking about to have the scanners, to have all of the people working there. But yeah, I'm sure you know the value's better.
Okay, I'm disappointed. I was about to move to Manitoba, to Winnipeg, but no, just okay. No, I'll stay in Switzerland. So sorry, guys. may I have one more question?
Yeah.
Yeah. So you identified about like 5-10 major parameters that some of them were redundant through the type of fractures, but some of the parameters that was identified are kind of a weasel parameters that you say, well, what the fuck, why they are there, and you try to find an explanation behind. Would it be worse to try to take those parameters and try to find what the underlying reason of why these parameters, and maybe have a more direct measure rather than using a surrogate of the cause? You know what I mean?
I do know what you mean. The thing about
so that will improve at the end. Would you improve then the model based on the first layout? Then you just pick those with kind of a weasel parameters, and then you try to explain the why, the cause, and try to go directly to the cause to feed the model and replace it by something more direct who can potentially give you more value.
Yeah, so for sure, if you get rid of parameters that are completely useless, then you get rid of noise. The extreme gradient boosting algorithm is pretty good at ignoring variables that are purely noise. I agree with you. If you get rid of variables that are proven to be completely garbage and just noise, that the algorithm will get better and more reproducible. However, the idea about getting rid of variables just because they're correlative and non-causative, the only time that that would really improve is if those variables didn't have any correlation in different populations. So for example, anxiety and benzodiazepines, the only time that that would be a problem that I can't give you the true reason for why those lead to fracture is if in different countries, for example, benzodiazepines didn't lead to falls. And so as long as people behave similarly from country to country, then it's not as much of an issue. And so my goal right now, at least, is to reassess this on 50,000 independent patients in Manitoba, and then potentially reassess it on some patients in BC and some patients in Ontario, because I think the majority of these variables will be quite similar from province to province in Canada. But yeah, ultimately, you're correct in one way, which is if you get rid of variables that are completely useless, then you can increase the reproducibility of the model in different locations. But one of the other reasons to get rid of useless variables is if somebody actually has to collect those variables. Whereas in this case, because those variables are being collected by some computer code, even if they contribute 0.0001% to the final model, those variables are essentially free to collect. And so what I've done here is try to let the artificial intelligence algorithm rule out which variables are useless and not try to do that as much using my human intuition, because all of the current models are already based on human intuition. And the second reason is all of these, as I mentioned at the beginning, all of these variables are in this data set because Bill has already thought about this for 30 years. So the reason these variables are in the data set is because Bill thought they might matter for one reason or another. And so that's one of the other reasons that I didn't work as hard to get rid of useless variables, because I trust in Bill. But you're right. I could probably get the model down to 50 variables similar to FREM and only lose like 0.01 area under the curve. And so, sure, I can look into that more right now because I have a model that works fairly well, and I like the underlying methodology of ensembling individual fracture predictions. I think that that has some base validity. I'm just going to focus on doing the economic analysis for now. And you're right. I removed some of the useless variables with the Baruda feature selection algorithm. And that is more important, I think, if I want to make the most parsimonious model. But right now, what I'm trying to do is just see what's a cutoff for any model, because it doesn't really matter what model I input. You're going to get a certain receiver operating characteristic curve. And so I'm just trying to focus on selecting the best cutoff based off the economic analysis, rather than trying to get another 0.01% in that. I've already put in, I would say, too much time on creating the current extreme gradient boosting algorithm.
Okay, thanks for that short answer again. Just to point out, one of the issues with the FREM, because it was agnostic and included all of those over 1,000 different codes, is some of the predictors at the end that came out as very strong. You just scratch your head over, like atopic dermatitis and pregnancy-related complications. So it does at least. You're right. You start out with at least with some variables that don't give you quite as much head scratching. Deepeng Zhang has asked a question by chat, and I'll just read it out for you. What do you mean by 90% collinear?
So basically, in this case, I only looked at the numeric variables. So that one's more important for my subsequent bone mineral density included And in that case, I took basically the bone mineral density variables, and then I just put them into a correlation coefficient. And then in that case, I just got rid of variables that were like 90% correlated. So in that case, I just took just like bone mineral density values rather than putting in bone mineral density and T-score and Z-score. In this administrative FRAX, almost none of the variables are, massively collinear. But so for example, some of the variables that are highly collinear are like survival probability and age. And then one of the ways that I dealt with that is just by putting those into the Cox proportional hazard model, rather than cranking them into the overall extreme gradient boosting algorithm. But yeah, you're right. That statement is more relevant for the algorithm that I'm working on right now that has all of the bone mineral density data, just because in that case, I think you actually are just introducing complete garbage by taking, essentially the same number processed in a slightly different way. And it gets computationally intensive to the point where I think you actually are just wasting time, because I don't think there's that much more lift to have, a T-score, Z-score, bone mineral density, bone mineral concentration, area, all at a single site in the hip. I think it's just pick one and move on. Thanks for that question.
Thank you, Mark. That's clear. So we still have time to ask another question?
Yes.
Sure.
So, we have so many kind of risk factors. Some are multiple, some are not multiple. So can you, based on these models, say you do some recommendations, say for this group of people, if you doing these things, you can reduce your risk factors by say 10% or how many percent? So is it doable, say for individual or group of individual? Say if you do these top 5 things, you can reduce certain % of your risk.
Do you mean by taking anti-resorptive medications, or do you mean by modifying?
Yeah. Some of the factors are modifiable. Yeah, like take some medication or other activities, or some are not modifiable, right? Yeah. So for individual, group of individual, you can, if you do this top 5 things, of course, it's valid by individual to individual or valid by group to group, you can reduce your risk of certain %.
Yeah, so I've been thinking about this as well. The last time I brought it up at a meeting, the person I was talking to was just like, why bother? But I agree with you. I think it would be great if I could say this group of people, if they take anti-resorptive therapy, will have a reduction by a certain amount. The only way I can think of to do that would be to take my current risk prediction using the model that uses all available data. So current bone mineral density and current risk factors. And then what I would have to do is take only the patients that have follow-up scans. So only the 60,000 patients. So I have calculated changes in bone mineral density. And I think the way that you would do what you're proposing is, I would, instead of trying to predict the fracture event, I would have to do a regression on the change in bone mineral density. And so I would take the current scan, and then I have a parameter called velocity of bone change compared to previous. So I would take the current scan, and then I would take the velocity of change per year compared to the follow-up scan. And then all I would do is I would take that numeric value and I would train my, 800 parameters in the complete model. I would train it based off of that change. And then I would see how accurate can I get the model at predicting that change. So the problem is, all that would do is tell you, do I think you're going to change? But to then go to the next level and try to identify, I guess you could do like 2 groups. You could do one where you try to predict how much they'll change without anti-resorptive therapy and how much they'll change with anti-resorptive therapy. But then the problem is you have a ton of bias, because those groups are totally different. So I think the short answer is that would be super challenging to have a clean data set. You could come up with a number, but I don't know how easy it would be to say, and therefore this group should get treated and this group should not, which is, I think, the reason that it's a bit more valid to try to say, this is what I think your fracture risk is today, and because I think it's high, you should get therapy. Another thing that I was talking about yesterday is there any way to look at the fracture date and then correct for the fracture date based upon information that you have available after the scan? So like, is there a way to try to come up with a way to see whether that fracture would have occurred earlier if they hadn't had therapy, or would that fracture have occurred later if they had had therapy? But yeah, long story short, super interesting question, very challenging, and I'll think about it more.
Thank you.
And on that, yeah, I think that was great. We're getting thanks from Carson for the presentation, and I think thanks from all the participants. We're at the top of the hour. The mark of a good